In RF engineering, signals are not only changing over time, but also interacting in phase and direction. A simple number is not enough to describe this behavior accurately. In this lesson, we will learn vector basics and how vectors help represent RF signals in a geometric and intuitive way. In basic electrical analysis, many quantities such as voltage, current, and power are treated as scalar values. These scalars are sufficient when signals are constant or vary only in magnitude. However, RF signals behave differently because they carry both magnitude and phase information simultaneously. When multiple RF signals interact, their behavior depends not only on how strong they are, but also on their direction in phase space. Two signals with the same amplitude can produce completely different results depending on whether they are aligned or shifted in phase. This is something scalar values cannot represent. Vectors solve this limitation by introducing direction in addition to magnitude. This allows RF signals to be represented in a more complete and physically meaningful way. A vector is a mathematical object that has both magnitude and direction. In RF engineering, this concept is extremely useful because it naturally represents signals as quantities that have strength and phase. Instead of thinking of a signal as a single changing value, we can represent it as an arrow in a two-dimensional plane. The length of the arrow corresponds to signal amplitude, while the angle corresponds to phase relative to a reference signal. This representation transforms signal analysis from an abstract time-based problem into a geometric problem, where interactions between signals become visual and intuitive. One of the most important properties of vectors is that they can be added geometrically. This property directly maps to how RF signals combine in real systems. When two signals are added, their result depends on both magnitude and phase difference. If two vectors point in the same direction, they reinforce each other and produce a larger resultant signal. If they point in opposite directions, they partially or completely cancel each other. This behavior explains many RF phenomena such as constructive and destructive interference, signal fading, and amplitude variation in communication channels. In RF systems, sinusoidal signals can be represented as rotating vectors in a plane. This is closely related to the concept of phasors and complex numbers, but vectors provide a more intuitive geometric starting point. As a signal evolves over time, its vector representation rotates at a constant angular velocity. The projection of this vector onto a specific axis corresponds to the observed time-domain waveform. This connection between geometry and time-domain behavior is one of the most powerful ideas in RF engineering because it allows engineers to visualize oscillations instead of only working with equations. In RF engineering, vector concepts are used in almost every area of signal analysis. Antenna radiation patterns, polarization, signal propagation, and interference analysis all rely on vector representations. For example, electromagnetic waves themselves are vector fields, meaning they have both magnitude and direction in space. Understanding vector basics is therefore essential for interpreting how signals propagate through physical environments. Vectors also form the conceptual foundation for more advanced tools such as complex numbers, phasors, and frequency domain analysis, which will be used extensively in later RF topics. In this lesson, we learned that vectors provide a geometric way to represent RF signals using magnitude and direction. They allow us to visualize signal interaction, interference, and phase relationships in a more intuitive way than scalar values. In the next lesson, we will explore coordinate systems and understand how different reference frames are used in RF analysis. If you found this useful, like the video, subscribe, and follow for the next lesson.